Locus and Ruth Horowitz are computational. So we saw how to do these computations, we saw how to make these graphs. And we're really not going to we're not going to touch on Nyquist and Ruth Horowitz this semester. That would be for a more advanced class. Let me just review for you the Bode stability criteria and before we go on, because this is really the fundamental basis of what we're doing for basically the rest of the semester. So the idea is we start with the open loop system. Open loop means we disconnect the loop right here. So this is disconnected. We start with the open loop system. And notice when I have the open loop system, a signal travels through GC, GV, GP, and GS. It just never comes back to here. So that's why we call G open loop, GP, GV, GC, GS. So notice that the open loop system, the so-called open loop system, includes the controller. It includes everything. So the open loop transfer function includes the process, the valve, the final element, the controller, and the measurement device. But it doesn't have this ratio, it just has this. And for the Bode stability situation analysis, the assumption, we assume that this is we need G open loop to be stable to apply Bode. Okay, so how does this work? So the idea is we start out and we introduce a sine function to SP prime. And the sine function, since everything is linear in this, we've linearized everything. Everything in each of these boxes is linear. When it passes through here, I also have a sine function. It may have a different magnitude, but it's still a sine function. It may have a phase shift, but it's still a sine function. Because we noted that this, when we have linear problems, linear transfer functions, when you put a sine function in, you get a sine function out, but it may have a phase lag and it may have a different magnitude, but it's still a sine function with the same frequency. So I have a sine function here, 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 and here. So these are all sine functions. But there could be a different magnitude and there could be a different amplitude. Now the amplitude is multiplied by the amplitude ratio of GC, GV, GP, GS, which is exactly G open loop. So when I start out with an amplitude, say 1 here, I come back with an amplitude AR of the open loop. Now, and again, there could be a phase lag. So I want you to imagine a situation where I start out this way, and eventually the system comes to steady state. So I have these sine waves everywhere. Now, at the next step, so that's step 1 is I have a sine wave. The next step is what I'm going to do is I'm going to tune the system. How do I tune the system? I tune the system by changing omega. Because we know that the phase lag could depend on omega. So I start playing with different omegas until I get to a situation where delta phi between here and here is equal to plus or minus pi. So let's do step 1. Step 1 is introduce sine SP prime tilde is a sine omega. And then that tells me that CV prime tilde M is equal to the amplitude ratio of the open loop times sine omega t plus phi. And this is at steady state. Now, remember, since this control loop, when I close the loop, calculates the error, and the controller is based on the error, I take SP prime tilde and I subtract CVM prime tilde. So once I'm in steady state, I change SP prime tilde to a constant, and I close the loop. Once I close the loop at SP prime tilde is a constant, then I have a sine wave coming in, a constant minus a sine wave. Now what happens when I have the minus sign? When I introduce the minus sign, the minima become maxima and the maxima become minima. So when I have a phase difference of pi, so actually here I should say 1a, tune phi, which is a function of omega, to be plus or minus pi. So when I close the loop, and I introduce the minus sign, all of a sudden, well, before I close the loop, notice that I've changed SP prime to a constant. So when I close the loop now, I'm going to have a constant minus this CVM prime, which is pi out of phase with the initial sign function. So now I have an error that's a constant minus this, minus something that was 180 degrees out of phase. Since it's minus 180 degrees out of phase, it's in phase. So it's the error is a sign function that's in phase with the original sign function. And now what happens, but it has magnitude amplitude ratio of the open loop system. Now once I close the loop, that signal goes through the loop again, gets multiplied by the amplitude ratio again, and shifted again by minus pi. When I come here and I subtract something that is minus pi out of phase, it becomes in phase and I add it. So what happens is that every time through, I have the original error which is equal to a constant minus AR of the open loop sine omega t. The reason why the minus cancels the pi. And now every time through the loop, I get multiplied by, so this thing is a sine function. Well, actually, it's minus sine omega t plus pi, or minus pi, which is equal to the constant plus AR open loop sine omega t. Because the minus here brings me into phase. This was pi degrees out of phase. The minus sign brings me back into phase. And that's again because if I have a sine wave and I'm pi degrees out of phase, this is sine omega t minus pi. If I take the negative of this, minus sine omega t minus pi, this brings me right back to here. So I'm flipping it again. Okay, so now every time through the loop, so the next time through the loop, I have this thing going through the loop, and it comes back multiplied, again, shifted by minus pi and multiplied by the amplitude ratio. So the next time through the loop, it's multiplied, so I have AR open loop. So I've got the constant C plus AR open loop times sine omega t. The next time through, it gets multiplied through by another AR open loop. The next time through, it gets multiplied by another AR open loop. And in principle, it goes through the open loop. It goes through that loop an infinite number of times. So what happens? I have a constant plus the sum AR open loop to the end, n equal 1 to infinity, times sine omega t. And this sum, well, this sum is finite only if AR open loop is less than 1. Because if I look at 1 plus epsilon squared as dot 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 to infinity, this is equal to 1 over 1 minus epsilon. Now you can see that in two ways. One way is you can take the Taylor series of this, or you can just multiply it by 1 minus epsilon. And you'll see that I have 1 times 1 minus epsilon times 1 plus epsilon. Minus epsilon squared plus epsilon squared. And they all cancel. So clearly, as long as epsilon is less than 1, this is finite. So as long as the amplitude ratio is less than 1, this adds up to a finite number. And even though it goes through the loop an infinite number of times, it becomes a sine wave of finite magnitude. I never go to infinity. On the other hand, if the amplitude ratio is 1 or greater, then this thing diverges. When it's 1, I get infinity. When it's greater than 1, this formula doesn't hold. And when it's greater than 1, this just adds up to infinity. So the stability criterion, if the amplitude ratio of the open loop system is less than 1, it's stable. If the amplitude ratio of the open loop system is greater than 1, it's unstable. So that's sort of a review of the Bode stability criterion. Any questions on that? I think I went into a little bit more detail today than I did last time. Okay, so what's the basic idea? How do we actually implement it? The way we implement it is we look at our system, we calculate G open loop, we check if it's stable. Otherwise, there's no need doing using the criterion. If it's stable, then I can use the Bode stability criterion. And then what I do is I calculate the amplitude ratio, and I calculate the phase lag. And we know from complex variables that the product of complex numbers, the magnitude of the product of complex numbers is the product of the magnitudes. So the magnitude of G open loop at I omega is just the product of each of the individual pieces, its magnitude at I omega. And we also know that if I multiply complex numbers, each one of which has a magnitude and an angle, or e to the I phi, that the angle for the product is just the sum of the angles for the individual ones. So phi of the open loop is phi of the individual pieces, and this is nice because that says I don't have to deal with the big messy equation. I can deal with each of the pieces, which is much easier, and I can put them together. And in fact, in your textbook, which you're supposed to have with you, in table 10.2, they list the transfer function, the amplitude ratio, and the phase angle, the formulas for various standard systems, first order, second order, proportional controller, integral, differential controller, PI, PD, PID, etc. So those are listed there. And these plots, the Bode plots, for these standard amplitude ratios and phis for these standard systems, a whole bunch of them are plotted for you in figure 10.13. So, and I'm going to be referring to this. So we have transfer functions, amplitude ratios, and phis in table 10.2, and we've got the plots, the Bode plots, in figures 10.13, and that's useful because, again, we can put together, if we know the Bode plots, or the transfer functions, for the individual pieces, this tells us how to put them together for a more complicated system out of all these little pieces. So so how do we do a problem? The way we do a problem is we look at the problem, we calculate GP, GC, GV, GS, GD if necessary. And then what we do is we put them together and we calculate G open loop, we calculate the amplitude ratio of the open loop, and phi open loop. And what we do then is we try to manipulate omega, tune omega, so that the phi is equal to minus pi. And what we did last time was we did a first order system where phi was the arctangent of minus 5w for this case. It was first order. The amplitude ratio was this quantity. And we did the plots. We did the plots clearly when, this should be I omega squared. This should be omega squared. So clearly, when omega is 0, this is just 0.039. And as omega gets very big, I can drop the 1, and I just take the square root, 1 over 5 omega, I get 0.039 over 5 omega. When I take the log of that, I get log of 0.039 over 5 minus log omega. So this just becomes a straight line of slope minus 1. Down here. So this is what the amplitude ratio looks like. And this we saw from a plot of the arctangent. This is 0. This is pi over 2, minus pi over 2, minus pi. But this looks like this. So that's what the arctangent looks like. And as you can see here, when omega is 0, this looks like the arctangent of 0, which is 0. And when omega goes to infinity, it looks like the arctangent of minus infinity. Well, that's just minus pi over 2. So it goes from 0 to minus pi over 2. So we can see for first order system, no matter what I do to omega, from 0 to infinity, I can never get to minus pi. I can never tune it to be minus pi. So this system is always stable. And we said that first order systems were uniquely very stable. It's only because it's first order. That's unusual. So what we wanted to do now is move on to second order systems, more complicated systems, and take a look at those. Are there any questions so far? Any questions? Is that clear? Okay, so let's look at a second order system. Do I want to put numbers in, or should I just do a generic second order system? Let's do generic second order system. Okay, so let's do a generic second order system. So, for example, one of these ones where I have 2 C stars in series, and what kind of controller do I want to put on here? Let's make this proportional only controller. Proportional only. So this is, say, a second order system. So in a second order system, then I have GP is KP. In this case, I'm going to set V1 equal to V2 over 1 plus, and I could have a first order reaction, K goes to product. 1 plus ST squared. I'm going to set GV equal to 1, GS equal to 1, and GC is equal to KC. So this is an example. I can choose anything I like. So if I do that, I find that G open loop is just equal to the product of these 4. So that's KC, KP, 1, 1 over 1 plus ST squared. Now, let's just look at the second order part of the process. So let's look at this particular quantity. So I'm just going to look at the open loop here. I'm not going to look at the closed loop. Okay, so what do we have for the amplitude ratio and for phi? Well, that we can just look up in this table. We don't have to derive it because we've derived it in the past. So if you look in table 10.2, for a second order system, I've got I've got KC, KB, and the amplitude ratio, here it is 1 plus omega squared T squared. It's the square root of that squared. We already derived that. And here I have the arctangent, twice the arctangent of minus omega. Okay, why is that? Well, remember, this one, this second order system, is just two first order systems in series. And if it's two first order systems in series, I just multiply the amplitudes together. So I take the amplitude ratio, which is 1 over the square root of omega squared t squared, and I multiply it by itself, so I get just the constant squared over 1 plus omega squared t squared, because it's the square root of squared. If I had different t's, if I had different volumes here, then it would be the square root of 1 plus omega squared t1 squared times the square root of 1 plus omega squared t2 squared. And the amplitude ratios, they add. So the amplitude ratio for one of them is the arctangent of minus omega t. And the other one, since it's the same volume, is also the arctangent of minus omega t. So that's just twice the arctangent of omega t. So let's just look at the Baudet plots for this. Log amplitude ratio, log phi versus log omega. And again, we could look these up, or we could just derive them. So here, this thing, again, when omega 0, this just starts out as KCKP. And as omega gets big, I can drop the 1, and I just have 1 over omega squared t squared. I take the log of both sides, and I have a minus 2 log omega. So this thing looks like it has a slope of minus 2. Okay, this thing is twice this thing. So it's the same shape, but the range is twice as big. So I go from 0 to minus pi. And what you can see here is I never get to minus pi. I need omega to be infinity before I get to minus pi. So again, I can't do my tuning to get to minus pi. Since I can never get to minus pi, I can never get the feedback to be additive. I can never, remember the additive feedback, positive feedback, is the worst case is when they add. If they're not exactly in phase, then they're going to start canceling. So if they're canceling, they're never going to add up to infinity. So this case is also stable. Because no matter what I do, I can never get it to its Baudet stable. Because no matter what I do, I can't get it to be 180 degrees out of phase. Any questions on that? Okay, let's look at another example. Let's look at example 1 with a delay. Do I want a delay? No, with a different GV and a different GS. Both of them first order. So GV, I want them both to be something over 1 plus S times something over 1 plus S times something. And I want this to be numerical. I'm going to make this a numerical example, so I need the numbers. Where did they go? Okay, so here I'm going to make it 5S, 0.039. Well, let's do the GV first. 1 plus S, well, I can just make this TV and TS, and then I'll give you numbers for them. So I make TV 0.033 and TS 0.25. So let's look at G open loop. So GV, GS, everything else is the same as example 1. This is example 1. So G open loop is equal to GV, well, it's equal to GP, 0.039 for 1 plus 5S, that's GP. GV is 1 over 1 plus S times 0.033. Times GS, 1 over 1 plus S times 0.039. And the other, and GV, GS, what else is there? Oh, and GC is just KC.
Because it's proportionally controlled.
Proportional under control. So let's look at the Baudet plot for this system. Now notice, here we had a first order system. It was first order. Here we had a second order system because G open L was open loop was second order. Now notice I've got three factors of 1 plus s times something in the denominator. So this is third order. So this is third order. We saw that first and second order were stable. What about third order? Well, again, I'm going to use these facts to determine what my amplitude ratio is. So the amplitude ratio for the open loop system. And remember, I'm doing the amplitude ratio for the open loop system because the Baudet stability criteria just depends on the amplitude ratio of the open loop system. So even though I have a closed loop, I look at the amplitude ratio for the, for the closed loop system, for the open loop system. All right, well, let's go ahead and do it. This is the amplitude ratio for this times this times this times this. So I've got 0.039 times Kc. They come along for the ride. And the amplitude ratio of 1 over 1 plus 5s from a first order system, you know, it's just this. It's divided by the square root of 1 plus 25 omega squared. This one, in a similar manner, is the square root of 1 plus 0.033 squared omega squared. And this one is, by the same calculation, 1 plus 0.25 squared omega squared. So that's the amplitude ratio. And how about phi? Well, phi is the arctangent of minus omega t, minus 5 omega, plus, because of course I add them, plus the arctangent of minus 0.033 omega from here, same formula, plus the arctangent of minus 0.25 omega. And let's just look at this. Remember, in the first order and the second order examples, things remain stable because no matter what I did to omega, I couldn't get less than pi over 2 here, and I couldn't get all the way down to pi here. So if I can't get to pi, then according to the Baudet criterion, it's stable. Well, this guy goes from 0 to minus pi over 2. This guy goes from 0 to minus pi over 2. And this guy goes from 0 to minus pi over 2. So when I add them up, in principle, there's the possibility that I could go from 0 plus 0 plus 0, which is 0, to minus pi over 2 plus minus pi over 2 plus minus pi over 2 is minus 3 pi over 2. So if I look at the log of the amplitude ratio versus log of omega, and the log of phi versus the log of omega. If this is minus pi minus 3 pi over 2, 0, actually, minus pi over 2, 0. And let's look at the amplitude ratio. The amplitude ratio, again, when omega is 0, this is 0.039 Kc. Then this thing, well, as omega goes to infinity, let's see what happens as omega goes to infinity. As omega goes to infinity, this just becomes 5 omega. This becomes 0.033 omega. And this becomes 0.25 omega. So I've got an omega to the 3 halves in the denominator. So this thing looks like, let's see, I'm sorry. Here I have an omega, an omega, an omega. I get an omega cubed. So this thing again is going to look something like this, where this now has a slope of -3, the limiting slope. Well, let's notice what's going on here. Now, depending on how these add, how these are shifted, I can change the shape. The shape isn't necessarily exactly like this, so you need to do the numerical calculation, which obviously I'm not doing exactly, I'm just taking out of the textbook, but what you get is something that looks like this. And in particular, you pass minus pi. You do go through minus pi. So what happens here? Now we can do the Bode stability criterion. So let's make this a little straighter, this one. So we look where the curve goes through minus pi. So we've tuned to be minus pi. That is, we found an omega that gets me at minus pi. And we presume that this thing, in this particular case, it doesn't come back up to minus pi. There's only one omega that gets me minus pi. And then what we do is we find this where the omega, where phi is minus pi. And we're going to call that omega critical. And then we go up. Here again is omega critical. To the curve, the amplitude ratio curve, and then we read across, and this is AR critical. And now we ask, is AR critical greater than 1 or less than 1? If it's less than 1, then stable. If it's greater than 1, it's unstable. But notice that the amplitude ratio in this case depends on Kc. So we can run the numbers for different values of Kc. So if we run the numbers for different values of Kc, what do we get? So here we have Kc, and here we have the amplitude ratio. So obviously, I'm not doing this calculation, I'm just taking it out of the textbook. If we take three values, 1, 500, and 6,000, for Kc, for the feedback control. In this case, in the first case, the amplitude ratio is 0.0002. In the second case, it's 0.1 or 0.01? 0.1. And in the third case, it's 1.2. So what's going on here? What we find, remember, Kc is setting the scale. This is 0.039 times Kc. It's just that Kc is setting the scale here. So when Kc is 1, then this is so small that this point down here is 0.0002. When Kc is 500, the scale is different, and this point is now 0.1. These are both stable. But when Kc is 6,000, then this point is 1.2. So this is, of course, unstable. So here you can see that if I make the feedback proportional only controller too aggressive, I pick Kc too big, then I go from stable to unstable. That's a concept we've seen before. Are there any questions on that?
What Pekin book is this?
I'm sorry?
This example is Pekin book.
Page? It depends what version of the textbook you have.
Second issue.
Huh?
The second issue.
I mean,
Or just like what example? Because examples are very
I mean, it's, what example is it? I don't know. It's, I mean, every version of the textbook is different. You just have to look for it.
Okay.
It's silly for me to waste time looking. I think it's example 10.7.
Okay.
Are there any other questions? Okay, why don't we look at another case, another situation. And here we're going to look at the influence of delay. If you remember, we said early on in the semester, practically in the first class, that delays make things less stable. And we gave the example of adjusting the temperature in the shower. And we saw that, or of driving any place in the United States, that would be the appropriate example, except for here, when you're driving and trying to stay in your lane. If there's a big delay between when you turn the wheel and what happens, chances are you're going to crash. So let's see how that plays out. So let's look at a situation where, again, I have a second order system. So I'm still going to look at this situation. Example, the same second order system. Same one as before, but I'm going to put some numbers in. So again, this is stream A, this is stream B, and as usual, we're going to make VA much less than VB, but XAA is much greater than XAB. That's the setup we've had before. We had it with 3 CSTRs in series, here we'll only do 2. What we're going to use here, again, I have a first order reaction, A goes to product, first order. And I'm going to use PI control, which means that C is KC times 1 plus 1 over STI. So this is not just proportional, but it's proportional integral control. It's second order, so GP is KP over 1 plus ST squared. And since it's first order, we remember that T is equal to tau, since I have a first order reaction, over 1 plus K tau squared. Well, that's T. No, it's 1 over 1 plus K tau squared. Let's do one thing at a time. That's tau, T, and Kp, and this is K, right, and Kp is equal to 1 over 1 plus K tau squared. So that's all from earlier in the semester. That's T and that's Kp. What else can we say here? So now I want to put in some numbers. So we're going to make the volume, some numbers, the volume 5, and the units are consistent. I'm not going to fuss about the units here. I'm going to make VB 5, so this is meters cubed. VB is 5 meters cubed per second per minute, okay? And why don't I just copy all the numbers? CA in is 20 moles per meter cubed. K, the rate constant, is going to be 1 per minute. And the valve is 50% open. So an KV is going to be 0.4, which we know is CA in over VS. And I'm going to set KC equal to 15 and T equal to TI equal to 1 minute. Okay, those are all a bunch of numbers. So let's calculate G open loop. G open loop. Again, G open loop, the Bode stability criterion depends on the open loop, so it's equal to the product of these 4. So GP, we say, is KP over 1 plus STP. Well, why don't we calculate some of these guys before I actually do that, since I need some numbers. Okay, so first let's calculate T. T is equal to tau. Tau is the volume of the volumetric flow rate, so it's 1 minute. Let's do this first. Tau is 5 over 5. Meters cubed over meters cubed per minute is 1 minute. T is equal to 1 minute over 1 plus 1 minute times k, which is 1 per minute, is 1 over 2 is a half. A half a minute. And again, that's consistent because when I have a reaction, I deplete the reactant faster than when I don't have a reaction. So that's why T is shorter than tau. We've seen that all throughout the semester. We should also calculate Kp. Kp is 1 over 1 plus 1 times tau, which is 1, squared is 1/2 squared is a quarter. So that's a quarter. So now I know what Kp is. So let's figure out G open loop. G open loop is Kp, which is a quarter, divided by 1 plus S times T. T is a half. Squared. That's Gp. Gv is just Kv. 0.4 times Gc, which is 15. Was there a question? I heard a noise. Over, here it is, times 1 plus 1 over S times Ti. But Ti we said is 1. Was Ti 1 or 0.1? I remember it not being 1. No, it's 1. Okay. 1 over 1 plus S. So that's Gp, Gv, Gc, and I guess I'll set Gs equal to 1. Gs. Okay, so this is 1 quarter of 0.4 is 0.1. 0.1 times 15 is 1.5 times, yeah, 1 plus 1/2 S squared times 1 plus 1 over S. Okay, so there we have it. And now instead of multiplying all that out, I can use this, this information here. Or what I can do, right now, I could do it the Baudet stability method, or I can just calculate the, since I only have one parameter here, well, I have no parameters. I have no parameters here. I can just use the root locus. So let's use the root locus. Because it's really easy here. I'm just going to get a polynomial in S. So I get 1.5 over 1 plus S plus 1/4 S squared. And here, this is going to be multiplied by, I multiply top and bottom by S. So I have 1 plus 1 over S. So I multiply top by S. So I have 1 plus S. And I multiply the bottom by S as well. So this is G open loop. But actually, I don't want just G open loop. I want the whole thing here. So let's do CV prime over SP prime. So I won't do this. I'll do it the other way using the root locus. So let's look at CV prime. And we'll go over SP prime. And this is equal to G open loop, well, G, P, GV, GC, over 1 plus GP, GV, GC, GS. And let's see what I get here. So this is, well, the numerator, the GS is a 1, so the numerator and denominator are the same. I have 1.5, 1 plus 1/2 S squared, 1 plus 1 over S, divided by 1 plus 1.5, 1 plus 1/2 S squared, 1 plus 1 over S, times 1. So here I have the extra GS. Okay, so now I'm going to multiply this out. So obviously I'm looking at a set point change here, not not a disturbance. And so I'm going to multiply top and bottom by 1 plus 1 over, already we're done? Okay. 1 plus s over 2 squared. And that's going to cancel here and here. So I have a 1 plus, as we did a minute ago, s plus s squared over 4. That's multiplied by the 1. So here I have a 1.5. And now I'm, so 1.5, and I have a 1 plus 1 over s. And here I have a plus 1.5, 1 plus 1 over s. And now what I'm going to do is I'm going to multiply top and bottom by s. If I multiply top and bottom by s, I have 1.5 s plus 1 divided by, when I multiply by s, I get an s cubed over 4 plus s squared times 1 plus 1.5, 2.5, plus s, no, I'm sorry, let's do this carefully. S times s is just s squared, that's fine. And then I have plus s times 1 plus 1.5 is 2.5 plus 1.5. So if I haven't made any arithmetic mistakes, here I have my cubic equation. And if I've done the cubic equation right, we can find the solutions to that cubic equation. And there are 3 solutions. So if I want to examine, remember, if I want to examine the stability using the root locus method, I look at the zeros of the denominators. So if I look at the roots of the denominator, they're kind enough to calculate it in your textbook. Let's just make sure I didn't make any mistakes in the, so it's a quarter plus 1 plus 2.5 plus 1.5. Yes, I even got the arithmetic right. Miracles do happen. So let's see what the roots are. The roots are minus 1.60 plus or minus 2.21i. So that's 2 of the roots, and since the cubic there are 3 roots, and the other one is minus 0.81. Now, of course, since this is a cubic with real coefficients, whenever I have a complex root, I need it and its complex conjugate. So when I multiply things together, the coefficients of the polynomial are all real. So therefore, I have to have one real root, it's negative, and the 2 complex roots both have negative real parts. So this is stable for these numbers. Therefore, it's stable. Any questions on that? Well, now let's look at what happens when I add to that a delay. But before I add to that a delay, I would like to just also do the Baudet. Let's do the Baudet as well. For the same problem. So notice for a second order system, that's this thing, we already did a second order system. So we know for a second order system, this was second order, that the amplitude ratio, well, we know that log 5, so for the GP part, we know that log 5, log omega, if this is minus pi and this is 0, then it never quite reaches minus pi. That's for the GP. Obviously for GV and GS, that's just equal to 0.4. That's just a constant. So if I want the, remember for a constant, if I want the arctangent of the imaginary part over the real part, well, this is real. The imaginary part is 0. So the arctangent is 0, which is just 0. So here, I just get 0, log 5 versus log omega. This is just always 0. It doesn't depend on omega. Finally, I've got the PI controller. PI controller I need to know what happens to log 5 versus log omega. Well, let's analyze the PI controller. I can just look it up in the table, but let's just do it quickly. So for the PI controller, PI, I've got, this is board 3. I've got GC is equal to KC times 1 over plus 1 over STI. And so let's look at GC of I omega. That's equal to KC, and let's multiply by STI. So I've got 1 plus STI over STI. So I just multiply top and bottom by STI. I multiply this thing by STI, numerator and denominator, so it's 1 plus STI over STI. And when I write this as I omega, I write it this way, and I want to get the I out of the denominator. So I multiply top and bottom by I. And if I do that, I have KC times I plus, well, I times I is minus 1, so I have minus omega ti divided by omega ti. And of course, here I have I squared, so I have another minus 1. So this becomes a minus here. And now I rewrite that. This is equal to, let's write the real part. The real part is KC, because this over this. And the imaginary part is minus I times KC over omega ti. It's a little bit of algebra, but nothing too serious. KC over minus. So let's look at the arctangent of the imaginary part over the real part. That's the arctangent of the imaginary part is KC over omega ti with the minus divided by KC, the real part. The KC's cancel. This is the arctangent of minus 1 over omega ti. So let's look at the limits, what this is supposed to look like. As omega goes to 0, this is the arctangent of minus infinity. The arctangent of minus infinity is minus pi over 2. So this thing, minus pi over 2, it's going over there. It's going to minus pi over 2. What happens when omega goes to infinity? When omega goes to infinity, as omega goes to infinity, this thing just goes to 0. The arctangent is 0. The arctangent of 0 is 0. So this thing goes like this. This is 0. So what I can notice immediately is when this thing is near 0, this is near pi minus pi over 2. So clearly, as omega goes to 0, I can't get lower than minus pi over 2. On the other hand, when this thing goes to minus, finally gets to pi, this thing's already 0. So I can't get lower than minus pi. So in this case, the Bode stability, and this thing adds nothing, because it's 0. So the Bode stability criterion agrees with root locus. It also says it's stable, because I can't get to minus pi. Is that clear? Okay, so what happens when I modify this example? To add a delay. And let's say the delay is, short. Just one minute. 1 minute. So what happens? That tells me that GP is the same thing as it was before, but it's multiplied by e to the I, e to the I, t, e to the I, the delay, e to the I theta. It was e to the minus I theta. E to the minus I theta. This was the delay part. E to the minus I theta. Times s. So here theta is just going to be 1. So here it's just going to be 1/4 over 1 plus 1/2 s squared e to the minus I, e to the minus I s. I think it's e to the minus theta s theta. That's what it was. It's been a while. E to the minus s theta. So here it's just e to the minus s. I could look it up, but I believe this was correct. So let's see what happens, what's going to change when I go to G open loop. G open loop is going to be the same thing, the old one, times e to the minus I omega. It's going to be the same one I had before, just times e to the minus I omega. So the first thing that this tells me, that I'm going to get, is let's look at the phi. So phi, we said, was these phi's I had before plus the phi of this thing. So let's look at the phi of this thing. Phi of this thing is the arctangent phi of the delay, because I multiplied something. So I don't have to calculate the overall. The way I calculate the overall phi is I just add the phi of the delay. So that's the arctangent of the imaginary part of this. This is, of course, G open loop old times the cosine I omega plus I times the sine of omega. So it's the arctangent of the imaginary part, which is the sine of omega, over the real part, which is the cosine of omega. The arctangent of the tangent is just omega. Of course, I can add any number of factors of pi I like, but let's just keep this simple. So that tells me that I have an extra factor of omega here, and this was actually of minus omega. So this is minus omega. So this tells me that phi now is phi old minus omega. Well, I'm going to write omega in kind of a pedantic way. Omega, this is phi old minus e to the log omega. And I did it that way because I'm plotting versus log omega. So let's look at what that looks like. So here's the log of phi of the delay versus log omega. So this is minus e to a power. Well, e to the x looks like this. I'll do it backwards. E to the x looks like this. Negative e to the x looks like this. So this looks like this. And even if I have a minus pi here, this thing is plunging down exponentially fast. So let's see. So when I add this to this, here I had a problem that when it wasn't a problem, it was a good thing. When I added all three of these, I could never get to minus pi. This thing gets to minus pi all by itself. So when I add that thing, what do I get? I get something that's really very minus pi. Let's see what the picture looks like. When I add them up, log phi total is dominated by this guy. It looks something like this. And it just keeps going, log omega. And let's look at the log of the amplitude ratio. So even if this is minus pi, we get there. And here's the log of the amplitude ratio. And let's just see where the amplitude ratio takes us. So the amplitude ratio, well, the amplitude ratio for the delay is just the magnitude of e to the minus I omega. Well, that's just the magnitude, that's just sine squared plus cosine squared. The square root of sine squared plus cosine squared is just 1. That doesn't add anything, but I didn't bother with this yet, so let's just get the amplitude ratio here. Well, obviously GV, GS, the amplitude ratio for GV, GS is just 0.4. The amplitude ratio for GP is second order, so we know what that is. It's just equal to this thing. So what is the amplitude ratio? So the amplitude ratio overall is equal to 1 for the delay. It's equal to 0.4 for GVGS. And now I've got GC and GP. So for GP, it was KP over 1 plus omega squared T squared. So it's 1/4 over 1 plus a half S quantity squared. And for GC, it was, I didn't bother calculating it, it's the magnitude of this guy. So it's the square root of this squared plus this squared. And this is I omega. Actually I should just write this as amplitude ratio. So it's 1/4, let's do the amplitude ratio. When I write it as an amplitude ratio, I've got a square root. So where's my second order problem? Yeah, well actually it was 1 over 1 plus omega squared T squared. 1 plus omega squared, and T, what was T here? T was a half. So this was, of course, for GP. And now I need for GC. Let's see what GC is. So GC is the magnitude of this thing. So I can factor out the KC. And KC we said is 15 here. 15. So I've got a 15 times the square root of 1 plus the square root of 1 plus 1 over omega squared Ti squared. Ti, what's Ti? Ti is 1. So there I have the amplitude ratio. That's the amplitude ratio. And if I plot this, so of course I have to plot this, and you can figure out what it is. Well, what happens at 0? At 0, this is 1, and this is 1, so I just get a constant. It goes to a constant as I go here. But what happens as omega goes to infinity? As omega goes to infinity, this thing becomes 0, and this thing, so this thing just becomes a constant. And as omega goes to infinity, this constant drops out, and it just looks like minus omega squared. So it looks like something that comes off as a straight line. So this says slope minus 1. And I can calculate the intercept. The intercept is going to be 1 times, so this is 0.1 times 15 is 0.1 times 15 is 1.5. And when omega is 0, it's just 1.5. This is 1.5. And then it starts going down slope minus 1. Okay, so what happens when we do our Bode stability analysis? Well, this thing crosses minus pi. This becomes omega critical. And then I look to see what this number is. Well, what you can see here is I get some value, whatever that value is. And it turns out that that value is 1.32. Turns out that value is 1.32. So that tells me, since this is greater than 1, so this is the amplitude ratio, AR critical. And since AR critical is 1.32 is greater than 1, this is unstable. Now I want you to notice here that if my delay were different. If my delay were less, well, first, if I had no delay, the system was stable. If my delay were less, so let's look at phi. If my delay were smaller, so instead of this being omega, it could have been omega over 2. If my delay were smaller, then I would have subtracted less. So what that says, if my delay were smaller, then my curve would have looked something like this. Let's see. I want to add, if I add something, yeah, then my curve would look something like this. So if I had subtracted less, then my curve would have been higher, and I would have crossed a little further out to the right, which would have meant I would have had a lower value of the amplitude ratio. So had I crossed a little further to the right, I would have had a lower value of the amplitude ratio, and then this might have been less than 1, and the thing would have been stable. So what you can see is that the larger the delay, the more I subtract. So here's a bigger delay. In a bigger delay, I make things even worse because I cross further to the left, and then I cross it even in a higher amplitude ratio. So what you can see here is that the larger the delay, the more unstable the system is. But a little bit of a delay doesn't have to make it unstable. And there's always a tiny delay, even in the shower when you turn the knob. It's not really instantaneous. There could be, a certain fraction of a second. That doesn't make it unstable. But as I crank up the delay, then things get worse and worse. Any questions on that? And you can see how these pictures help and how these two relations make our life much easier. They make our life really easier because we don't have to look at the whole mass at once. We just look at each of the individual pieces, which we can get from the table, from those charts on figure 10.13, and we can put them together this way. And we get the amplitude ratios from the table, table 10.2, and we get these pictures, Baudet plots, from figure 10.13. Are there any questions on that? Okay, so I'm not sure I can use this part of Blackboard because of the glare. Can you see here? You can. Okay, so I can use that part of the Blackboard. All right, so, oh boy, time flies when you're having fun. We only have a few minutes left. So, some notes. I want you to note, by the way, I'm going particularly slowly today, going through lots of examples. Not because I don't have more material to cover, but this is crucial. This is really important, and I want you to learn it, so I'm going through examples. I can tell you read the examples in the book, but I'm doing it out loud so you can ask questions, not that you've asked questions, but I'm adding more explanation than you get in the textbook. So one note, what happens if Kp is negative? What if Kp is negative? Well, when I count Kp, what does that mean? Sometimes I turn a knob, I increase something, and the thing I'm interested in goes down instead of goes up. That's okay, that happens. So for example, let's say let's say there was a disturbance, and the disturbance, lowered or increased the flow rate of or why don't we say it lowered the concentration of the reactant. Well, then I'm going to have a lower concentration of reactant at the output. So Kp can be positive or negative depending on the situation. Well, when I calculate an amplitude ratio, notice an amplitude ratio is a magnitude. So an amplitude ratio is always non-negative. It's never negative. So whenever I have Kp that's negative, then I always have to use the magnitude of Kp. So that tells me my Gp, which is going to be a kp times some stuff. First order, second order, anything else. When kp is negative, then what I want to do is I want to write this as the magnitude of kp times e to the I pi over stuff. So since kp is negative, I'm going to take the negative out because e to the I pi is minus 1. Because it's the cosine of pi. Cosine of pi is minus 1 plus I times the sine of pi. Sine of pi is 0. It's just minus 1. It's another way, a nice confusing way of writing minus 1. So then the rest of the analysis is the same. Except, in the end, when I'm calculating phi total, I've got phi for positive kp, and this is just another factor in there. So this other factor is plus the phi of e to the I pi, and the phi of e to the I pi is plus pi. So I always, and actually I think I write this as e to the minus I pi, so I have a minus pi. So it subtracts pi from phi. E to the plus pi, e to the I pi, and e to the minus I pi are both minus 1. So notice I subtract pi when I do this. So, that means I'm lowering the curve by an amount of pi. So when I lower it by an amount of pi, if it never went below 0, now it never goes below pi, minus pi. If it never went below minus pi over 2, well, now it will go to minus 3 pi over 2, which is where it was here. If it never went below minus pi over 2, if kp is negative, it can go down to minus 3 pi over 2. So my chances of a first order system with a negative kp can reach minus pi, whereas with a positive kp it can't. For any given system, that doesn't mean it's unstable, that just means that you have to do the calculation. Because you can do the calculation, find omega critical, and when you go to the amplitude ratio curve, you still could have something less than 1. So it could still be stable, but you have to go through the details. What else can we say? Lots of things. Okay, so I made the point that if I subtract, the more I subtract from the phi curve, from this curve, I can subtract it by a delay, I can subtract it by having a negative kp, I could have other things in the system that end up, other contributions that might be negative. The more I subtract, as long as the amplitude ratio curve is monotonically decreasing with log omega, the more I subtract, the more unstable I make it. Now, of course, that again depends on the amplitude ratio Baudet plot being monotonically decreasing. So if I subtract more, that means I cross minus pi earlier, so that means I hit this curve further to the left and it's higher. So it could be more unstable or less stable. Let's look for a second at the integrator system. I think this is the last thing I'm going to get to do today. Let's just look at the pure integrator. The integrator had GP as 1 over AS. So GP of I omega is 1 over A I omega, which I multiply top and bottom by I, and I get minus I over A omega. So let's look at this. The amplitude ratio, AR, for an integrator is the magnitude of minus I over A omega, which is just 1 over A omega. That's no big deal. And how about the phi? Well, phi is the arctangent of the imaginary part over the real part. The imaginary part is minus 1 over A omega, and the real part is 0. So it's the arctangent of something over 0, minus 1 over A omega over 0. So the arctangent of minus infinity is minus pi over 2. So we say the arctangent of minus infinity is minus pi over 2. Okay, wonderful. So that tells me that the Baudet plot here, so let's log phi versus log omega is just a constant, minus pi over 2. So if I have an integrator, I just get minus pi over 2, so I can't do my Baudet stability analysis. And my amplitude is 1 over a omega. What happens if I put this in an integrator with proportional control? I don't know why this box is here. That is not convenient. Okay, so what happens in that case? Well, then I also need GC. GC is KC. So let's look at G open loop. That's equal to 1 over AS times KC. And what do I want to do here before I run out of time? Let's look at CV over SP. CV prime tilde over SP prime tilde. So that has an open loop in the numerator because GS is 1 here, and GV is 1. That's KC over AS over 1 plus KC over AS. And let's look at what happens here when for the amplitude ratio and phi. So let's look at phi. So I have the amplitude ratio is the magnitude of Kc over AI omega divided by 1 plus Kc over AI omega. And so we can see what that is. I multiply top and bottom by AI omega over Kc. So I have 1 plus AI omega over Kc. And I need to get that the I out of the denominator. Well, we know this is 1 plus something times omega. That's just like a first order system. So in the first order system, so that looks just like the first order system. And in the first order system, we know that phi, because it's something, 1 plus omega times something. So we know that phi is equal to the arctangent of minus A omega over Kc. And the amplitude ratio is 1 over the square root of 1 plus A over Kc omega quantity squared. So it looks just like the first order system. And so let's notice what this thing looks like. Log phi versus log omega. So it's just like the first order system. It looks exactly like these guys for the first order system. So what you can see here is here by adding the proportional control, I went from something that had phi is equal to a constant to something that looks like phi in a first order system. And I think there was a comment I wanted to make about that. Okay, and with proportional integral control, it's going to look a little different, but I haven't ran out of time, so I will get to that. Are there any questions? Remember, there were homeworks due today, and homework due Wednesday. The other thing to note is I looked at the calendar, and there are 2 more classes. There's Wednesday and Monday, and then comes everyone's favorite week, final week. And apparently, our exam is the first day of finals week. So it's a week from Wednesday. So it's a good idea to start reviewing control. Again, if you have any questions, I come early, I just noticed this morning someone wanted to, couldn't make this the early time and wants another time, so I'll answer that when I get back. If you can't make the earlier time, we can always make a special time. I think, again, if you ask, we can arrange problem sessions. But you have to ask, someone has to ask, you have to ask, and then we can have problem sessions. The last thing I want to do is schedule something when no one shows up. Now, of course, you could wait until the day before the final, or you could schedule a problem session earlier. But you guys have to make the first move on it. Are there any other questions?